Okay.
Yeah. All right, so our project was on dimensionality reduction for snake robot trajectory planning. What that means for us is we're trying to build a library of motions for bypassing obstacles. And to do that, we're going to use some dimension reduction techniques to try and bring this down into a problem that we can apply machine learning to. So one example of a trajectory like this would be getting a snake robot to move past a rectangular beam. The first step in our dimension reduction was to take this continuous trajectory and parameterize it in a way that allows us to simply optimize over a set of parameters over an entire trajectory instead of an entire trajectory. The technique we use to do that is called dynamic movement primitives. For the purposes of this, all we really need to worry about is that we have some parameters theta I that describe the shape of the trajectory for each joint. We have n of these parameters per DMP. We have 16 joints, and so we've reduced it from 16 continuous trajectories down to 16 times n parameters that we need to optimize over. To do the actual optimization, we decided to use what's known as policy improvement with path integrals, or pi squared. This is a technique that was designed specifically to work well for DMPs. The way pi squared works is it will randomly perturb your parameters many times. You do many different rollouts. And from those rollouts, you're going to evaluate a cost function and do a weighted update of your parameters based on those rollout costs. You continue to do this until you get convergence. And from there, you perform one final rollout and go, all right, here's your final trajectory. One of the benefits of this approach is that we can actually define the cost function in terms of task variables. So a task variable for us is something like the position of the snake robot relative to the beam. That's not something that we have a direct mapping from theta to our task variables. And so we're not able to actually analytically compute any sort of a gradient. We need some sort of a gradient estimate, and this is what pi squared is providing for us. One of the downsides to doing this is that we no longer have something that's guaranteed to be convex. We have no idea what the mapping between theta and these task variables is. We can't use any of the convex guarantees. And so the initialization of the parameters is going to have a large impact on our ability to actually get good results. So what we did to initialize our parameters is actually manually move the snake robot past the beam and recorded those trajectories. Now, clearly, the fact that our hands are on the beam, our hands are on the snake, that's going to have some impact on the actual dynamics. And so we can't just do that once and call it good. There's also the consideration of some noise in the whole problem. And so we're trying to optimize, not just get past the beam, but do so robustly. So we've taken the problem and we've turned it from a continuous trajectory optimization to a parameter optimization. But for the trajectories we're looking at, we're still looking at a total of 480 parameters to optimize. 480 is a ridiculously large amount of parameters. Pi squared's been proven to be able to manage that, but we'd like to do better. So the idea is, can we take that 480 parameters and reduce it even further with other dimensionality reduction techniques? The first step we tried was principal component analysis, where we take our trajectories in joint space, turn them into trajectories in a latent space, do our learning, our optimization there, and then back project into joint space and evaluate in task space. We also did a similar process with variational Gaussian process latent variable models. You can think of that as PCA, but with kernels in a similar way to Gaussian processes do kernel regression. When we first started, one of the big challenges that we were running into is that the existing infrastructure limited us to working on one computer with one process at a time. But pi squared is something that is embarrassingly parallel, to quote Manziel. So we decided, can we do better than that? We ended up improving this algorithm to be able to command multiple different computers across the lab network, each one performing a single rollout, and then aggregating those results together. All right. So the results we found were not promising, but they're interesting. If you take a look at our plots, you can clearly see that the PCA jumps at the beginning and then does decay away to a similar result to the baseline, but it never quite beats it. Similarly, the GPLVM doesn't even come close. In fact, you can see that we aren't even doing anywhere near the number of rollouts. And that is because we found the computational complexity of doing the GPLVM meant that that's about as many rollouts as we could do in the same time frame as doing roughly 4,000 rollouts for the other algorithms. So what you're seeing here is a comparison of results for similar amounts of computation time. The initial costs you can see are also different, but that's to be expected given we're actually, in a sense, throwing away a little bit of data. We were hoping that was noise. Turns out it might not be. All right, so despite all of this, it only really matters if it works on the snake robot itself.